This is Knowledge Engineering with Semantic Web Technologies, Lecture 3, Ontologies and Logic. This is the last part, or the last official part of this lecture, part number 10, where we talk about the Tableaux algorithm for ALC, which is one of the most simple description logics. So, the Tableaux algorithm, as you might remember, is a decision procedure which works for some kind of logic. So for positional logic we have learned it, for first order logic we have learned it. And what we do first is we want to recapitulate shortly how it works before we adapt it to description logics. Because we know in description logics we have to adapt it. Simply we have other kind of connectors that we have to take care of. And the other thing is, of course, we have to adapt it since we know from first order logic, because they are semi-decidable, probably this algorithm won't stop or won't terminate for description logic. So, okay, but first the recapitulation. So the Tableaux algorithm is a proof algorithm to check the consistency of a logical formula by inferring that its negation is a contradiction. So this is a kind of proof by refutation. We have talked a lot about this. So we have simply to assume the inverse of our original problem and have to show that this is a contradiction. And we do this in the Tableaux algorithm by constructing a tree, so the so-called tableau. And each node in that tree is marked with a logical formula, and the path from the root to a leaf is usually followed in a conjunctive way. So this is a conjunction of all formulas represented within the nodes in the path, and a branch represents a disjunction. And usually this kind of graph or tree is created with a successive application of the so-called Tableau extension rules. And we learned several of the rules that can be applied for propositional logic or for first-order logic. So, for ALC first, we have to bring the class definitions in our knowledge base in a specific form, in the so-called negation normal form, which supports the following assumption that the negations within our knowledge base, they should be placed directly in front of atomic classes. And of course, this is not always the case if you look at the knowledge bases. So therefore, you try to transform your knowledge base with the help of logical equivalencies to a knowledge base in so-called negation normal form. So let's assume we have a knowledge base W, and first thing we have to do to bring W, or our knowledge base, into a negation normal form is we have to get rid of equivalencies and subsumptions. And this is quite easy. We know already that we can substitute an equivalency by two subsumptions. So if C and D are equivalent classes, this means that C subsumes D and likewise D subsumes C. So this is easily substituted. That's the first equivalency we have to consider. The next is, of course, we have to substitute the subsumption itself. So if C is subsumed by D, this is logically equivalent with the expression not C or D. So this means this is the disjunction of the two classes not C and D. And you can prove that these two expressions are logically equivalent. We know this already if it comes to implication, for example, and propositional logic. And then, after that, you have to take care that the negations that you created or that are in your knowledge base must be put somewhere in front of atomic expressions, and therefore you have to apply these so-called NNF transformations, these negation normal form transformations that you see on the right side of the screen. So these are also equivalencies, and it means that, of course, the negation normal form of an atomic expression C, of course, this is C, and the negation normal form of the complement of an atomic class C, of course, is the complement of C. Then the next negation normal form covers the double negation, because double negation, of course, then you come up with the original class, and then you have you split here, for example, disjunction and conjunction, simply to put the negation normal form then in front of the classes itself. So disjunction and conjunction. If then there is a negation involved, so if you are considering the negation of a disjunction or the negation of a conjunction, you can apply De Morgan's rules to put, again, the negation inside the braces of your expression, and then you have only to take care that here the polarity of your connector will change. So a disjunction becomes a conjunction becomes a disjunction. And then, of course, you have to take care of the quantifiers that are available in description logics. We know at ALC we have special quantifiers that are restricted to the restriction of the range of roles. So as you see here, you say here, for example, for the universal quantification, which is a strict coupling, and you have here the existential quantification with this loose coupling here. There, the negation normal form, if no negation is involved, is quite simple. So you simply go then inside the bound classes, inside that relation. And if a negation is involved, you put the negation inside the scope of that quantifier. And if you do that, of course, according to the logical equivalence rules, the polarity of the quantifier also is changing. So a not for all becomes it exists, and then in the end not. So, and vice versa. Not exists becomes for all not. So like you see here in the equivalences for the negation normal form. And then the resulting knowledge base is the negation normal form of W. So, and of course both W and the negation normal form of W, they are logically equivalent, with the property that the negation always is placed then directly in front of atomic classes. Let's have a look at an example. So here we have a simple expression in description logics, and we want to translate that into negation normal form. So first thing we have to consider here is, of course, we have a subsumption, and we simply substitute this subsumption here with the disjunction. And the first part of the subsumption has to be negated. So this is the first line. Next part, of course, we have here a disjunction to consider. So this means first we take into account the negation normal form of the first part of the disjunction, and then the negation normal form of the second part of the disjunction. Then you see again, you have here lots of disjunctions, and the first thing we have a negation normal form of a negated atomic expression, and of course this is simply not P. So this is already solved. We already have, or we only have to take into account the rest of this formula. So okay, what we do here with the rest is we also have a disjunction, and this can also be broken down in two negation normal forms of, again, two expressions of which the first one is a conjunction and the last one is a disjunction. So first we take a look at the conjunction here. So the conjunction, of course, can in the same way split, and then we have the normal form of the first part and the second part of this conjunction. And then if we take into account the negation normal form of the following disjunction, we have to take into account that this disjunction has or is negated. So we have to apply here De Morgan's laws, and then we have to consider the negation normal function of not, so the double negated E, and then the negation normal function of negated D. And then again, it's quite simple. So the negation normal function of atomic expressions can be substituted by these atomic expressions. So like you see here in the first part, and then you of course can make use of the double negation rule. So the negation normal form of not E is the negation normal form of E, and this in the end, of course, is an atomic expression, and this is the end, in the end, the expression you come up with if you apply this kind of transformation on the original complex subsumption statement you have here. So this is some effort, of course, you have to invest before you can apply the Tableaux algorithm. And then there comes the most complex, or so the most important part, the new Tableaux expansion rules for ALC, for the attributive language with complement. And here I have expressed it not in the descriptive form you are used to in propositional logic or first order logic. Here I have made a more formal definition. So here we are talking about knowledge bases, and usually Tableaux expansion rules, they are used to derive new A-box facts. A-box, you remember, assertional knowledge has to deal with individuals. So usually let's consider a knowledge base which consists of the T-box, the terminological knowledge, and the A-box, the assertional knowledge. So first thing you can always do is, of course, A-box facts can be added to the Tableau. So if A is a member of C, then you can add it to the Tableau, or likewise, if A and B are connected via a role or property R, then this can also be added to the Tableau. More interestingly, if we consider a T-box, then, of course, all T-box axioms can be instantiated with known individuals and also sometimes with new individuals if there are no individuals at all, for example, and this can be added to the Tableau. So this means you can populate your A-box with new facts that can be derived from them with the help of these expansion rules. And then there are rules when to deal with more complex expressions, so with conjunctions, disjunctions, existential quantification, and universal quantification. And of course, we are considering description logics, therefore it's a little bit different. I mean, okay, here the conjunctive rule is exactly the same like the alpha rules we have considered. Or here the disjunctive rule also is, from content-wise, the same like the beta rule we have considered. But of course, here it's written in a more formal way. So if we consider that if the conjunction of two, let's say, complex classes C and D instantiated with an individual A is part of the A-box, and likewise the facts that A is a member of C and D is a member of D are not part of the A-box, then you can extend your existing A-box with the instantiation of C and D with this individual A. So this is like, of course, the alpha rule, like you know that, but here applied on description logics. For the disjunctive rule, it's quite the same. So if the disjunction of two complex classes C or D that are instantiated with an individual A are part of the A-box, and of course C of A or D of A are not part of this A-box, then of course you can create two new instances of that A-box, A prime and A double prime, which are on the other hand extending the already existing A-box with each instantiation either of C of A or D of A. So this splits here, this makes a disjunction. More interesting then here is the rule for existential quantification. So consider we have in our Tableau here or an expression with existential quantification, so loose restriction on a role and a class, and this is instantiated with an individual A. Then if there is no B such that B is a member of this class C, where we do this range restriction, and there is also no existing or instantiated relation between A and B, then our new A-box or the extension of our Tableau computes simply by extending the Tableau with the instantiation of the class C with a new individual, here set, and of course the instantiation of a relation with A, which has, of course, to be in relation with this new individual set, because this is exactly what here also this existential quantification in ALC really means. If I say there exists something which is connected to A via the relation A, and this has the class C, what this existential quantification says, then we simply translate that and extend the Tableau accordingly. More interestingly then, we can look at the universal quantification rule. There it's exactly the same, only we say that, of course, this holds for all. This is a strict binding. The only difference we have to do here or have to take into account here is, of course, we have to take into account existing individuals, because this should, of course, hold for all. If we look at the existential rule, then we, of course, you keep in mind the open world assumption, we can assume the existence of a new individual. So this is the extension, the existential quantification. For the universal quantification, of course, we could also use a new individual, but of course we should take into account the existing individuals simply because this assumption should also hold for all existing individuals. And if there is a contradiction, of course, maybe it's the easiest way to show it with already existing individuals. So this is the reason why we are doing that. And then we are simply extending the tableau here with a class membership definition of this individual B, because we simply say this holds for all individuals which are combined with A within the role R, like here the universal quantifier in description logics, the strict binding says. So all that are combined with that should be of class C, so therefore also B which already exists in A. But you will see this more closer in the examples, and no worry, we will also exercise this a lot then. So here again, if we want to apply the Tableaux algorithm, so we apply, of course, these expansion rules. And of course, you can do this in any order. There is no ordering for that. So this means the Tableaux algorithm is somehow non-deterministic, also simply because of the disjunction. So you go in both directions at the same time then. And if it happens that you close the tableau, this is the same like in propositional logic or first-order logic, then the original knowledge base is unsatisfiable. And of course, you only select elements that lead to new elements within the tableau. Otherwise, you don't use these rules to come up with elements that already exist, because you know that this is futile. You want to introduce either new elements and want to extend your knowledge base to find a contradiction there. And if it's no more possible to extend the knowledge base any further, so if these conditions that things that could be deduced already exist in your knowledge base, like we saw on the last page, then the algorithm terminates and the original knowledge base is satisfiable. So you cannot show that it's unsatisfiable by closing the tableau via these clashes or contradictions. You don't have a contradiction, you can apply any more extension rule, then you have to say, okay, my knowledge base that I have extended here is satisfiable. So this makes it quite easy to check the satisfiability of some ALC concepts. So what you do here, simply you use the Tableaux algorithm. And the input here is the ALC concept in negation normal form that you want to prove. And the output then would be true, which means yes, it is satisfiability if there is a clash-free tableau where no more rules can be applied. Otherwise, it would be false because you have found a contradiction. Then it's not satisfiable. But this is only checking the satisfiability of a concept. Taking care about all our other inference problems that we have introduced recently, you have to show that the according transformation of the original inference problem to unsatisfiability really holds. And then you can check this with the help of the Tableaux algorithm. We will do, again, some examples. So consider the following T-box example here. We have in a T-box, we state that professor is something, so it's either a person and person, a professor is a person and likewise a university employee, or a person and not a student. And from this knowledge base, which only contains a T-box, we want to show whether it can be entailed that a professor is a person. So we want to prove the professor subsumes the concept person, and this should be a logical consequence of the existing knowledge base. And the question is this working or not? So what we want to prove here is that the knowledge base combined with the negated assertion is unsatisfiable. Yeah, you remember that from our last part of the lecture. So what we have to do, of course, is then this extension of the knowledge base with a negated concept, so not professor subsumes a person. this has to be put first into negation normal form. So we know also the procedure. Here we transform the subsumption in a disjunction accordingly, and then we have a negation, and this negation leads to the application of the De Morgan rules, and in the end we come up with the concept professor and, so conjunctively combined with not person. So in the end we come up with a new T-box, T prime then, which holds both facts now in negation normal form. So I haven't shown you how to transform the first fact we have in our knowledge base, but this is quite easy. So there is only one negation in there, which is in front of an atomic concept, so you don't have to take care about that. And you have a subsumption which can simply be transformed into this disjunction. And then also for this disjunction, all negations that are there are in front of atomic expressions. Therefore, everything is settled, and we have a new T-box, T prime here, which contains these two new concept definitions. So, what to do next? We want to use the Tableaux algorithm for ALC to show whether this holds or not. So, let's simply try. The first thing we can do, so we don't have an A box, we instantiate this T box, because we say, yeah, of course, this should hold at least for some person. So, okay, we instantiate that for person A. This comes from the knowledge base. So this is the knowledge base extension. And we use first more simple fact. So this is simply that professor and not person. So here the conjunctive rule can be applied. And as you see here, we apply the conjunctive rule on the first row here, and we can deduce from that, or we can extend the tableau with A is a professor and A is not a person, which is quite simple. Okay, next thing we want to do, we can also instantiate the longer expression we see here and simply say, okay, for person A it also holds that exactly this expression can be applied on person A. Yeah, sure, we want to show that, of course, the knowledge base does not contain a contradiction. So therefore, we have to assume that this also, or the facts in the knowledge base, both hold for this individual A. Okay, so this is a more complicated expression. What we can do here, or what we see here, this is definitely, these are two disjunctions. Therefore, we have to apply first the disjunction rule. And I take first care of the first part here, which connects the not professor with the rest. And of course, we can deduce from that longer fact that A is not a professor and the rest. So this is in parallel, again, here a disjunction. So what we see already here, fact number 5, A is not a professor, and fact number 2, A is a professor. This is a contradiction which closes this branch of the tableau, and we only have to look at branch number 6. Branch number 6, again, we can apply the disjunctive rule, which again leads to a disjunction into two branches, and of course the first branch here covers a conjunction. Likewise, the second branch also covers a conjunction. And then I can apply here twice the conjunctive rule. So from the fact that A is a person and a university employee, of course, I can extend with that the tableau that A is a person and A is a university employee. And likewise, I can do it on the other side from the fact that A is a person and not a student. I can, of course, extend the tableau that A is a person and A is not a student. And here, of course, we see it here, as we already have stated, that the first branch here is closed, and also the other two branches will be closed because we have the statement in row number 3 that A is not a person, and we have in row number 9 A is a person, and in row number 11 A is a person. And so all branches of the tableau are closed and no new branches can be opened. So therefore we have shown the unsatisfiability of the knowledge base that we originally had. And therefore we have shown the opposite, which means we have shown that a professor also is a person, and that this holds, and that this can be deduced from the already existing knowledge base. So therefore we have applied the Tableaux algorithm to our original reasoning problem, where we wanted to find out whether a professor is also a person. Okay, this becomes, of course, more complicated if there are also quantifiers involved, especially which is bad if you look at the existential quantification, because with the existential quantification and the open world assumption, you always can assume the existence of additional individuals. So let's have a look at that. So we have a knowledge base and a T-box, and the T-box states that we have a concept which states not person or, and then has a parent which is a person. And we want to deduce from that knowledge base that Bill, an individual, is not a person. So you see here we have T-box and A-box. So in the A-box must be, if we want to prove that Bill is not a person, we will have to extend the knowledge base with its inverse. So we have to extend it with the fact that Bill is a person. So in the resulting knowledge base you have here in the T-box, not person, and there exists has parents, which is a person, and in the A-box it states Bill is a person. So let's start with our Tableaux algorithm. First of all, I take the A-box fact into my Tableau. Then I simply extend the T-box or apply the T-box to my already existing individual B and say, okay, this should of course also hold for Bill. And here I see a disjunction, therefore I can apply the disjunctive rule. So I can deduce from that that Bill is not a person, and of course Bill must have a parent which is a person. So with Bill is a person and Bill is not a person, this branch is closed. So let's have a look at the existential quantification. Here we state that Bill has a parent which is a person, which means, okay, we can say or can infer there must be a new individual, we call it here x1, and this is the parent of Bill. And simply because of the restriction to the class person, we can also conclude that, of course, x1 must be a member of the class person. So what to do next? So yeah, there are not more facts in the T-box. So what we can do again, of course, is we can extend the T-box with the individual or an instantiation of here our new individual x1. So we apply simply x1 to the fact that is in the T-box and say, okay, so this already held for Bill, so it also holds for x1. Yeah, we see this is a disjunction, and of course we can split the path and we can deduce that x1 is not a person, which closes that path. And on the other hand, we can also say, okay, yeah, there exists somebody who is the parent of x1 who is also a person, besides other things. Okay, the situation becomes more complicated if our knowledge base also contains quantifiers, especially if it contains an existential quantification. Keep in mind, we are dealing with the open world assumption. This means, with the help of the existential quantification, we can always assume the existence of a previously unknown individual. So let's look at an example. Here we have a knowledge base with a simple fact. So the T-box here has the fact not person, or there exists somebody or which is my parent, which is a parent, and of course is a person. What we want to deduce, we want to show that Bill is not a person is a logical consequence from that knowledge base. Of course, it's not necessarily a logical consequence, we can see that. But, of course, we can prove it with a Tableaux algorithm. For that, of course, we can extend our existing knowledge base with a negation of exactly this class membership. So the negation would then be Bill is a person. So what we have here is, okay, then a knowledge base consisting of a T-box and then of an A-box which states Bill is a person, which is the logical negation of the consequence we wanted to show. So and on that knowledge base, this new one, we can apply the Tableaux algorithm. So let's do that. So first of all, okay, we can put in the Tableau what we have in the A-box, and here we can say Bill is a person. Next thing we can do, we can of course apply or instantiate our fact we have in the T-box also with the individual we have in the A-box, because it should also hold for this individual. So therefore, we instantiate the T-box fact simply here also with our individual Bill. And we see that this T-box fact is a disjunction, so we can apply the disjunctive rule, which says that Bill is not a person, and we can see, yeah, this branch can easily be closed. The other branch contains the existential quantification, which says that there is somebody, it is a person, and this is the parent of Bill. So what we do, we assume the existence of a new individual, let's call that X1, and this is the parent of Bill, and X1 is a person. So that's quite nice. So how do we go on? We can further now extend, again, we have a new individual. We can extend the T-box we have and can instantiate the T-box with the new individual, can instantiate it with the new individual X1. So this means, okay, the fact applied to X1 again holds, and this is a disjunction, and I can again apply the disjunctive rule, which states that X sub 1 is not a person, therefore I can close also this branch. Then I have again an existential quantification, which says that X1 has a parent, and this new individual, let's call it X sub 2, this is also a person. Okay, how to go on? We have a new individual, therefore we can instantiate the knowledge we have in the T-box with this new individual. Therefore we have again here instantiate our assumption about X2. This is again a disjunction. We can apply the disjunctive rule. We can say, okay, X2 is not a person, and therefore this branch can be closed because we also have X2 is a person. This is a contradiction, or this is a negation. So therefore this branch is closed. You see, again, we stand here with X2, and of course we can subsume here that X2 has a parent which is also a person, and so on and so on. So here is the point reached where no termination is possible, because we can always deduce the existence of a new individual, and so on and so on. So the situation is like that. We always apply exactly the same extension rule, and of course there is no new knowledge created. So that's the point. We simply deal with, let's say, an open world and a potentially infinite universe, and therefore we can assume the existence of new individuals, and we will never come to an end. So this is an artificial situation that we should try to terminate, of course artificially, with a technique which is called blocking. So we can use blocking here simply if we say, yeah, there is no new knowledge to be created, and this does not further help to close the tableau. So we are looking for some technique, some formalism that we can, in a case like that, say, okay, the tableau terminates, it's not closed, we have not shown that this is a contradiction, so this means the original assumption that you see here must be somehow satisfiable. So, yeah, and we do it in the following way. So we are using for that the so-called class extension function for an individual, and this is the function sigma. And this function sigma simply enumerates all classes of which this individual it is applied on is member of. So for example, sigma of Bill is all the classes from the tableau you see up there where Bill is member of, and this of course is the class person. It's also then the more complex class, not person, or, and there exists somebody whose parent is a person, and of course the other one, there exists somebody whose parent has a person. So these are the three class expressions for which we had instantiations for Bill. Then we look for the next one that we have introduced with this existential quantification, which is X sub 1. And we also look at the class extension of X1. And we see here exactly the same classes, also person, then the complex one, and then the existential one. And if we can say that the class extension of a newly introduced individual is contained in the class extension of an already existing individual, then we can say this already existing individual blocks the newly introduced individual, and we can terminate the algorithm. So this is the termination procedure of the Tableaux algorithm. So in the end, the selection here of an existential quantification rule or a loose binding in a Tableau path A is blocked if there is already an individual B for which the class extension is a superclass of the class extension of our new individual A. So this is what we just showed. And then you have two possibilities of termination. First, if we are nevertheless able to close the tableau, so when there is no blocking, then of course the knowledge base is unsatisfiable and we are done. On the other hand, if you only can stop the algorithm by using that blocking, then the knowledge base is satisfiable. And this is also the same if all non-blocked selections of the tableau don't lead to an extension, so if you cannot apply any other extension rule. So this is the general extension of the Tableaux algorithm. And with that, of course, you can prove the unsatisfiability, or as you see here, the satisfiability of a knowledge base, and you can apply that to all kind of logical inference problems, which we will also do in the exercises for that course. And this closes lecture number 3. Now you know how to apply a mechanized reasoning algorithm also to description logics. Furthermore, in this course, we have several extra parts. So if you are interested in, you won't get scores for that. So you can look at the 3 extra parts of that course. We will talk about canonical forms. We will talk about another reasoning algorithm for first-order logic. And we will also make a short excursion into the history of ontologies. But you can also continue with lecture number 4, so with the 4th week of the lecture, when we will talk about OWL, rules, and reasoning.